In this video, what we're going to be doing is learning how to multiply matrices. In the last video, you learned how to multiply a scalar or a number times a matrix, but in this video, what we're going to do is learn how to multiply one matrix times another matrix. We're also going to learn about a special matrix called the identity matrix, and finally we're going to learn how to take a system of equations and express it using matrix multiplication. When we're multiplying matrices, what we're doing is we're taking the rows of the first matrix and we're multiplying it times the columns of the second matrix. Let's look at a super simple example where our first matrix just has one row and our second matrix just has one column. What we're going to do is we're going to multiply corresponding elements and then add them all together. So for instance, we're going to take this 3 times the 4, 3 times 4, and we're going to add that to this 2 times the 1. I'm sorry, negative 2 times 1. So that's where that is. So we multiply those corresponding elements and then we add them all together. Again, what we're doing is we're taking the 3 and we're multiplying it times this 4, and then we're adding to that negative 2 times 1. When we do that, we get 12 plus negative 2, which is 10. So this was a really easy example, and we're going to make it a little bit more complicated, but before we do that, let's make sure we understand what types of matrices it's okay to multiply. Because we're multiplying these corresponding elements, you have to have matching numbers. Now notice that the number of numbers in here that I needed to match up with the numbers here, I needed 2. So I had one row here that was 2 columns, and this matrix, the second matrix, had 2 rows but 1 column. And these two numbers had to be equal in order to be able to pair up the numbers correctly. The number of columns in your first matrix has to equal the number of rows in your second matrix. And when we get done, the size of our product is going to be a m times p. So if I have m by n, this has to be n times p. And the size of our answer is going to be m times p. So let's see exactly how that works. Notice here, my first matrix in this second example is a 1 by 2 matrix, and the second matrix is a 2 by 2 matrix. Now, these two numbers are equal, and so I can match things up properly, which means I can multiply these matrices, and my result, my size of my answer, is going to be a 1 by 2 matrix. To find this 1 by 2 matrix, what I'm going to do is I'm going to take this first row and I'm going to multiply it by the first column. That's going to get me the element in my first row, first column. So I have 3 times 4, that gives me that. And then I have negative 2 times 1, that gives me that. Now let's look for the element that's in row 1, column 2. I'm going to take row 1 and multiply times column 2. So I'm going to have 3 times 2, that's what I have here, and negative 2 times 5, that's what I have here. So when I do this multiplication and then simplify things, 12 minus 2 is 10, and then 6 minus 10 is negative 4. So again, just to recap here, what we're going to be doing is we're going to be taking the rows of the first matrix times the columns of the second matrix. Now, this process might seem really odd, but it actually makes sense in a lot of contexts. Let's go back to that video game sales problem that we did in the previous video. where I gave you the sales data for the month of October for 3 different stores. So in our sales matrix, our columns were our stores and our rows were our different types of game systems. And what we had to do in the last video was figure out what the revenue was for the Linwood store in October. So we know that PS4s sold for $300, Xboxes also sold for $300, and Nintendo Switches sold for $250. So to compute the revenue, we just needed to take our $300 for our PS4 and then multiply by the number of PS4s, that was 55, plus we had $300 for the Xbox times the number of Xboxes, that was the 40, and then $250 for the Nintendo Switch, and then multiply by the number of Nintendo Switches, and we got 25. Notice what we're doing is we're multiplying the second column of our matrix here times some numbers. If we take our price data and make this price matrix and put it here as our row matrix, we are multiplying by that second column, and that's how we got that 34,750. Let's see if we can come up with the revenue for the Northgate store and the revenue for the Everett store. The Northgate store, what we're doing is we're taking $300 per PS4 times the number of PS4s, that's 80, plus $300 times the number of Xboxes, that's 60, plus 250 times the number of Nintendo Switches, and that's 20. Notice I'm taking row 1 of my first matrix and multiplying it by column 1 of my second matrix, row 1, column 1, and so this number here is going to go right there. This element here, this is in row 1, column 3, and so to compute that element, what I would do is I would take this row 1 of this first matrix times column 3 of the second matrix. I would have 300 times 75 plus 300 times 60 plus 250 times 15, and this would be the revenue for the Everett store. Let's look at a slightly more complicated one. First, I'm asked to multiply matrix A times matrix B, and let's just check our sizes. So matrix A is a 2 by 2 and matrix B is a 2 by 2. So we need these two numbers to be the same, which they are, and this is the size of my matrix. So I made myself a matrix here where I had holes in 2 rows, 2 columns. To compute the product or the elements in each spot, what we're going to do is we're going to take our rows of our first matrix and multiply it by the columns in my second matrix. Let's start with row 1, column 1. So I'm taking row 1 and I'm multiplying it by column 1. So I'm going to have 3 times -4 plus -1 times 3. For this element, this is in row 1, column 2, so I'm going to take row 1 times column 2. So I'm going to have 3 times 5 plus -1 times 0. This element here is in row 2, column 1, so I'm going to take row 2 times column 1. I'm going to have 2 times -4 plus 5 times 3. And this element here is in row 2, column 2, so I'm going to take row 2 times column 2. So row 2 times column 2. 2 times 5 plus 5 times 0. So if I do this multiplication, I should end up with the following matrix. So negative 12 plus negative 3 is negative 15. 15 plus negative 1 times 0, that's 0, that's going to be 15. Negative 8 plus 15, that's going to be 7. And 10 plus 0, that's going to be 10. So let's do B times A. So now notice that I've written the two matrices side by side because that's going to help me keep track of things. And in order to find this element here, this is in row 1, column 1, I'm going to take row 1 and I'm going to multiply it by column 1. So I'm going to have negative 4 times 3 plus 5 times 2. This next element, this is in row 1, column 2, so I'm going to take row 1 times column 2. I'm going to have negative 4 times negative 1 plus 5 times 5. This element here, this is in row 2, column 1, so I'm going to take row 2 times column 1, so I'm going to have 3 times 3 plus 0 times 2. And then our last element is in row 2, column 2. So I'm taking row 2 times column 2. I'm going to have 3 times negative 1 plus 0 times 5. We end up with, let's see, negative 12 plus 10, that's negative 2. Negative 4 times negative 4 is, negative 4 times negative 1 is positive 4 plus 25, so that's 29. 9 plus 0 is 9. Negative 3 plus 0 is negative 3. Now, one thing to notice here is both times I ended up with a 2 by 2 matrix, but these two matrices are not the same. We are used to them being the same when we're multiplying. For instance, if I take 2 times 3, this equals 3 times 2. That property is called the commutative property of multiplication. But when we have matrices, A times B may equal B times A, but it's not guaranteed, and usually it's really lucky if that happens. Let's look at a couple more examples. Here we have our matrix A and our matrix B. This time they're different sizes. So let's first check to see if we can actually multiply them. Matrix A is a 2 by 3 matrix, 2 rows, 3 columns. Matrix B is a 3 by 2 matrix. These numbers match, so I can multiply them. My result is going to be a 2 by 2 matrix. So let's make a 2 by 2 matrix here. I've got 2 rows, 2 columns. Let's start by finding this element here in this first row, first column. So I'm going to take the first row times this first column. So I'm going to have 1 times 3 plus 4y times 2 plus negative 3 times 1. This next element here, this is in row 1, column 2, so I'm going to take row 1 and I multiply it by column 2. So I'm going to have 1 times negative 2 plus 4y times 1 plus negative 3 times 0. Let's move on to row 2. So now I have row 2 times column 1. So I'm taking row 2 times column 1. So I'm going to have x times 3 plus 0 times 2. I'm just going to not write that one. Plus 2 times 1. And then finally, when I have row 2, column 2, I'm going to take row 2 times column 2. So I'm going to have x times negative 2 plus 0 times 1 plus 0 times 2. Our final answer here is going to be, let's see, we have 3 plus 8y minus 3, that's going to be 8y. This element here is going to be negative 2 plus 4y. This element here is going to be 3x plus 2. And then this element here is just negative 2x. Let's look at another example. This time, instead of doing a times b, we're doing b times a. So let's write these so that they're side by side. That always makes it easier to do. And before we just start multiplying, let's check to see if we can actually do it. Matrix B is a 3 by 2 matrix. Matrix A is a 2 by 3 matrix. These numbers here, they're the same, so I can do it. And my resulting answer is going to be a 3 by 3 matrix. So let's make a matrix here that's got 3 rows and 3 columns. So let's start by doing row 1, column 1. So we're taking row 1 times column 1. I'm going to have 3 times 1 plus negative 2 times x. Now let's do row 1 times column 2. That's going to be 3 times 4y plus negative 2 times 0. And then let's do row 1, column 3. We're going to have 3 times negative 3 plus negative 2 times 2. Now let's move on to row 2. So this time, let's make this yellow. We're taking this yellow row and we're going to multiply it by all 3 of our columns. I'm going to take row 2 times column 1. So that's going to be 2 times 1 plus 1 times x. Row 2 times column 2 is going to be 2 times 4y plus 1 times 0. And row 2 times column 3 is going to be 2 times negative 3 plus 1 times 2. Now let's move on to row 3. So row 3, we'll use this green color. We're going to have row 3 times column 1. We're going to have 1 times 1 plus 0 times x. Row 3 times column 2 is going to be 1 times 4y plus 0 times 0. And row 3 times column 3 is going to be 1 times negative 3 plus 0 times 2. If you simplify, this is what you end up with. Let's look at a special matrix. This matrix is called the identity, and we have this in regular multiplication. The number 1 is a special number because if we take 1 times any other number, we get that other number. 1 times 3 is 3, 1 times 7 is 7, 1 times negative 11 is negative 11. So 1 times anything just gives you that same thing back. We have a similar thing for matrices. If we have a matrix that has 1s on the diagonal, 0s everywhere else, should look familiar from when we were doing those row operations. That matrix is a special matrix, and when we take that matrix and multiply it by any other matrix where the multiplication works for the size of the matrix, we're going to end up with what we started with. So let's just double check that. So if I have a 2 by 2 matrix and I multiply by another 2 by 2 matrix, I'm going to end up with a 2 by 2 matrix. So this is my I, this is my A. So let's take this 1, 0 times that first column. So I'm going to have 1 times 3 plus 0 times 2, that's going to be 3. Multiply by the second column, I'm going to have 1 times negative 1 plus 0 times 5, that's just negative 1. Multiplying the second row times that first column, I'm going to have 0 times 3 plus 2 times 1. And then the second row times the second column is going to give me 0 times negative 1 plus 1 times 5, or 5. So we end up with the same exact matrix that we started out with. So we can do this for matrices of lots of different sizes. These identity matrices are always square, and they have the same sort of pattern. They're always 1s along the diagonal and 0s everywhere else. One thing that's going to be helpful and we'll see this in the next section, is if we can take a system of equations and rewrite it using matrix multiplication. And the way we're going to do this is think of it in three different parts. We can take our coefficient matrix, multiply by our variable matrix, which is a column matrix, and get our right-hand side. Let's just double check this. So I'm taking our coefficient matrix times my variable matrix, and this is going to equal my right-hand side matrix. Let's look at the right-hand side. That's really easy here. That's going to be 7 and 11. My variables in this problem are x and y, so that's going to be x and y. And then my coefficients are the numbers in front of our x and y. That's going to be 1, 1, and then 2, 1. If I multiplied this out, I would have a 2 by 2 matrix times a 2 by 1 matrix, and this is a 2 by 1 matrix. Notice that these numbers match. This is the size of my answer. If I multiplied, taking this row times that column, I would have x plus y, and then here I would have 2x plus y, and this would equal 7 and 11. And if two matrices are equal, their corresponding elements have to be equal. So I would have this x plus y equals 7, which is that first equation. And then I would have 2x plus y is 11. That's that second equation. Here's a problem written in matrix multiplication, and what I want to do is rewrite this as a system of equations. Let's first think about our multiplication here. This is a 3 by 3 matrix. This is a 3 by 1 matrix, and it is legal to multiply those because those numbers match. My answer is going to be a 3 by 1 matrix. Let's start by multiplying those two matrices. If I multiply this first row times that first column, I'm going to have A plus 3B plus 2C. The second row is going to give me 0A plus 2B plus 4C. And the third row is going to give me negative 2A plus B plus 5C. And this has to equal 1, 4, 2. So my system of equations would look like A plus 3B plus 2C is 1. 2B plus 4C is going to be 4, and negative 2A plus B plus 5C is going to be 2. That's it for this video. Hopefully you found it helpful.